Okay, I think we are ready to get started. It's just gone past the 3:30 time. So welcome everybody. My name is Mike Fletcher. I'm with Laser 2000s and I'm really pleased to be co-hosting this session with our partners, Liquid Instruments, and in particular, our colleague, John Miller, who's going to give you a run through shortly about the abilities of the Moku products. So first of all, let me tell you a little about us. If you don't mind advancing on a slide for me, please, John. Thank you very much. So Laser 2000s, we've been working in this industry for 32 years now. We're very close to a lot of academic partners. We're proud to say we support pretty much every university in the UK and Ireland. And we're very well known for a number of photonic solutions, ranging really from filters, motion control. We get involved in a lot of applications, particularly imaging and spectroscopy. And our mission's always been to get best of breed partners from across the world and provide them into the UK. And Liquid Instruments very much fall into that category. So we work closely both with industrial and academic research partners. I think a lot of people on this call will be very much on the academic side of things. And we work closely from a postgrad position all the way up to professors in the labs. And we recently created a new team, a uni team, who have focused in on being close to universities, getting to the heart of what requirements are needed, and making sure people are well aware of things like the Moku product line that Liquid support us with. So if you can flick forward a slide for me. The easiest way to say it in some ways is everything on that table we can supply for you as Laser 2000s. We get involved in the wide range of products for our partners and customers to help them with their requirements, be it creating, detecting, or moving lights. That's very much where we get involved in. We're big in research and development, as I mentioned, both academia and industry. And the most important thing we have is we want to look after our customers, and we hope that being in business for 32 years is a good sign of that care for our customers. And if we look at, if you want to advance forward a slide for me, if we look at our partnering with Liquid, of the 32 years we've been in business, it's great to say that the last 8 of those we've been partnered with Liquid, and we've really enjoyed watching them grow, bringing new products to the market. And now we help them position with the Go, which we quite often see being used as a teaching tool, all the way up to the Pro, which has more and more features and functionalities coming on board, and offers a great way of replacing multiple instruments with a single unit. And their pioneering approach using a really intuitive GUI has really seen them stand out. So it's been exciting to watch them grow. And we're starting to do more things like this webinar, which you've given up your time for today, where we can help you understand some of the technology behind it. So the last thing I'll speak on is something we are really excited to kind of tell you guys who have joined the session for us. We're actually going to ask you to fill in a survey afterwards. And one of the people who fills it in, we picked at random, and we're delighted to send you a Moku Go as a thank you for participating in the webinar itself and giving us your feedback, so we can continue doing these and do them to the best standard we can for helping you get the most from it. So please do tell us how you find this next hour, and one of you lucky people will get a Moku Go as a result. But with that in mind, I'm going to hand over to John, who's going to pick up from me and go into much more detail. So John, over to you.
Thank you very much. Good afternoon, everyone. I'm John Miller. I'm an application engineer working with Liquid Instruments. And in my role, I help customers throughout their journey with our products, both before and after purchase. And my background is in physics and mathematics, in particular, a lot of interferometry for gravitational wave detectors, and some LiDAR sensors for mobile applications and in the automotive industry. And it's my pleasure to present this webinar on the Pound-Drever-Hall locking technique. So we'll start off with a quick introduction, why lasers are useful, different techniques for locking them and stabilizing them to cavities, including the Pound-Drever-Hall technique. I'll then give what I will hope will be an intuitive view of the PDH technique, so you can gain more of a feel for how the signals will change as you change parameters in your experiment. And I think even for experienced users, this might be useful. I'll then go through our laser lock box instrument and give a quick demo on some real hardware. And at the end, we'll have a Q&A. So we'll take these at the end. You can submit them in the Q&A interface in the webinar or in the chat, and we'll get to those in a little while. So let's start. Lasers are extremely useful in many fields. They have a short wavelength, 1,000,000 times smaller than radio waves, for example. And you can use this wavelength like a ruler in metrology applications. Using advanced techniques, you can even split the wavelength, like interferometry or digital phase meters. The short wavelength also means that the lasers don't spread out very much as they propagate. So you can shoot them around to send this ruler for making measurements to different places, or to make measurements over distance. Also, lasers interact with matter, which can be, sometimes it's a problem, but sometimes it's also very useful. So they're essential in a wide variety of applications. For example, optical clocks, where you're probing a stable atomic transition. Spectroscopy, as I said, lasers interact with matter, so you can look at absorption spectra, detection of traces of some substance within a gas or other medium. Communication in fiber, obviously, but also over free space. That's becomes quite hot recently. Gravitational wave detection. So by measuring small distances here on Earth, or indeed in space, you can measure the collisions of black holes that happened billions of years ago, look at exploding stars, lots of interesting astrophysics. And closer to home, with, for example, the GRACE mission, looking at the distance between two satellites which are chasing each other in orbit around Earth. You can infer the mass distribution on the surface of the planet. And this is really due to water moving around. So things like the polar ice caps melting and climate change, you can really say something meaningful about that by making measurements with lasers. But of course, lasers can be noisy. In particular, in this talk, we're looking more at frequency noise. And that noise can be sort of fundamental, coming from things like quantum effects or thermal noise in electronics. But it could also be due to the environment, like temperature, humidity, vibrations. So the solution is that we want to stabilize the laser. And there are lots of ways you can do this. One might be stabilizing to an atomic transition. For example, like a Heine laser stabilized to iodine. You can stabilize to another laser if you have something that's more stable. But often people stabilize their lasers using a cavity. And just to keep things concrete, that's the application I'm going to focus on today. So what is an optical cavity? There are lots of names for it. People call it a Fabry-Perot, an optical resonator, an etalon. I'm going to call it a cavity. And what it really is two partially transmissive mirrors facing each other. And if we have our laser and it's incident upon this system, we can look at the power transmitted on this photodiode and the power reflected on this photodiode. And if we plot the transmitted power here as a function of laser frequency, we see that there are these peaks at very particular frequencies. And this is really a resonance effect. So if the light coming in is in phase with the light that's circulating, the power inside the cavity will build up and you'll get these resonances. In reflection, so you have dips at the same frequencies, kind of conservation of energy or destructive interference. And in reflection, you also have phase steps of 360 degrees. when you go through a resonance. So the length, the frequency that resonates in the cavity depends on the length. And if the length is stable, then the frequency which resonates will be stable too. And if we're able to tune our laser to be on or close to one of these resonances, then the frequency of the laser will be stable. So stable cavity, stable resonances, stable laser. Okay, quick recap. Lasers are very useful, but they're noisy, and therefore to make high precision measurements, we need to stabilize them. Lots of ways to do this, but today we're going to focus on optical cavities. On the right here, this is a diagram showing a modern high-performance cavity. And you can see the lengths that people go to isolate against thermal effects, acoustics, vibrations, to really keep the length of that cavity stable. Okay, so how can we lock our laser onto this resonance, or keep the laser close to this stable resonance? There are many ways to do it, and I'm going to go through a few of them now, obviously finishing with PDH, but let's start with one of the most simple methods. So we have plotting the power transmitted through the cavity as a function of frequency in blue here. And if we introduce some reference voltage, this could come from a battery, it could be another photodiode sampling the output of the laser. And if we subtract these two signals, we get the error signal here shown on the bottom. So we see that the error signal is 0 here, where the reference crosses the power, and it's positive on one side, negative on the other, and almost linear. So you could use this for closed loop control to keep your laser on the side of this fringe. This is good, very simple, easy to do, but because we're on the side of the fringe, there are lots of noise couplings. And so one of the main ones being coupling to the power in the laser. Also, we're operating at low frequencies here. So in general, noise goes up at low frequencies. So you want to try and make your measurement up at high frequencies so the noise is low, and that's not what we can do with this technique. Also, you can only lock on the side of the fringe. I think if if this is your error signal and it's the same, it goes in the same direction, whether you're higher or lower than the resonance frequency, you don't know where you are. A technique which solves that problem is what I call dither locking. Some people call it top of fringe locking. Others, frequency modulation spectroscopy, even though we're not really doing any spectroscopy. But lots of names. What's really going on is that we modulate the frequency of the laser. That's represented by this orange curve here. And we look at the response in blue. So modulate the laser frequency and look at the modulation in the power transmitted through the cavity. We can do this at many detunings from resonance. There are lots of different frequencies around the resonance. And you'll see that the response shown in these little insets here depends on the gradient or the slope of the curve. So over here, if we modulate the frequency, we get a small response, it gets bigger, it gets even bigger. But then when you come to the peak, it's 0 because the gradient here is 0. At least the response at the modulation frequency will be 0. Then on the other side, it's the same story, but there's one important difference. So if you're below resonance over here, increasing the laser frequency makes the power go up. Conversely, on the other side of resonance, increasing the laser frequency makes the power go down. So if you look very closely, you'll see that the phase of all these signals are different. And what we can do is we can use phase-sensitive detection. So a lock-in amplifier would be an example of this. To get the amplitude and phase of all these signals. And if you look, the bottom pane here, the bottom axis, I'm plotting the error signal as a function of laser frequency. And you can see the correspondence between the response and the size of the error signal. So it's small, gets bigger, 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 then goes to 0 right on resonance. And then it's the same thing on the other side, but with the opposite phase, the opposite sign. So in this way, you can derive an error signal. You're really sort of getting the derivative of that transmitted power. But here, the error signal is 0 right on the center of resonance. So with this technique, you can lock right on resonance, and it's linear, bipolar, and you can use it to perform closed loop control. Difficulties with this technique, it can be hard to realize a high bandwidth and therefore high gain, so the noise performance might not be that good. And also you're really, when I say modulating the laser frequency, you're really moving the laser around, so you sort of broaden the laser line. Another way to do things is to use polarization. So what we can do here is we send some combination of polarization states into a cavity, and we engineer it so that one of these polarization states is resonant and the other is not. And because one is resonant, it will see the response of the cavity. So I showed earlier the phase change when you go through resonance and reflection, that phase change will be imprinted on that polarization. And then what comes out will be an elliptical polarization. So if you sent in something linear, what comes out will be elliptical. Then using polarization tricks, you can detect this ellipticity. And the key is that the ellipticity is different above and below resonance. And with that, you can derive an error signal, which looks much like the one on the previous slide. The question that comes up here is, why is one polarization resonant and the other one is not? And the answer is you need a birefringent cavity. So the classic example, they just put a linear polarizer in the cavity. So the polarization parallel to that polarizer will resonate and orthogonal will not. You can also use a triangular cavity where different polarization modes resonate at different frequencies. You can have birefringent optics, either on purpose or by accident. Maybe you stressed it in some asymmetric way, but you need a birefringent cavity. So this is another nice technique. It's pretty simple, no modulation or demodulation. It lets you lock on the top of the fringe, but you do need that birefringent cavity. A similar method is to use higher order spatial modes. So whatever laser beam you shine onto your cavity, it will be decomposed into the basis of modes of that cavity. So say I have my red beam here and I shine it onto the cavity. I think that's a nice round, perfect fundamental 0-0 laser beam. But in the basis of the cavity, it might be some lowest order mode, great, but also a higher order mode. And these higher order modes could be there due to, from the point of view of the cavity, mode mismatch, misalignment, a beam which is not round, etc. And if your cavity is stable, these different modes don't resonate at the same frequency. So what you can do is, around the resonance of this fundamental mode, the one that you usually care about, the higher order mode will be reflected from the cavity. It won't see any response, and it acts as a stable reference to which you can compare the other mode. You do this using split photodiodes or using apertures or knife edges to clip the beam. And again, with this technique, you get the similar looking dispersive type error signal. You can lock on the top of the fringe, linear, etc., etc. But again, we're working here at low frequencies. So if you are feeding back at audio frequencies, then all the audio noise in your setup will couple in there. Okay, now we arrive to Pound-Drever-Hall. This is sort of the canonical setup here. So we have a laser beam and we pass it through a phase modulator. Phase and frequency modulation are essentially the same thing. So you could be modulating your laser. But I've got a phase modulator here, and we can think of this modulation process as imprinting sidebands onto the light, and we'll see that more a little bit later. This carrier with two sidebands then interacts with the cavity, and using polarization tricks or even just a simple beam splitter, we get the light back onto an RF photodiode. This RF photodiode detects power. It's a diode detector, so we don't really see the optical field. We're just looking at power, and that's kind of an important point. The output of the diode then goes to a mixer, and a mixer is just a multiplier, and we're multiplying two signals, one from the photodiode. The other one comes from the waveform generator that you used to drive your modulator. So say this is a 10 megahertz sine wave to give you your sidebands. That's what goes into the other input of the mixer. In between, we have a phase shifter. We'll talk about that again more later. But that could be an actual box with switches, or you could just use a length of cable to give yourself a phase shift. The output of the mixer goes to a low-pass filter, and that is your Pound-Drever-Hall error signal. And then you're free to use that with a servo to feed back to your laser to keep it locked on or close to resonance. So what's really going on here? So we have a carrier and two sidebands, and when the carrier is close to resonance, we engineer it ideally so that the two phase sidebands are far from resonance, and they're effectively reflected. Then the response of the cavity is imprinted onto the carrier. And at the photodiode, we look at the beating between these fields. And what that looks like is shown here on this plot. So we have the photodiode signal as a function of time. And you'll see you have an oscillation at the modulation frequency. And as you pass through resonance, its amplitude changes. It gets bigger, bigger, bigger. And then the phase flips. And then it goes big, big, big to small. And this is analogous to what we saw with the dither locking technique. So if we use the same kind of thing, phase sensitive detection here, which is what we're really doing with the mixer and the low pass filter, we can pick out the kind of envelope of this signal and use that as our error signal. And that's what's plotted here. So the blue is the power on this photodiode in transmission through the cavity. And the orange signal is the PDH error signal. So you can see it's, as I've said 10 times, linear, bipolar, 0 at the center. So it's excellent for closed loop control. A few points about PDH. So you'll see there are lots of components here, lots of discrete components, at least with traditional equipment. And this can make the setup quite expensive, and it can be quite cumbersome to set up, take up a lot of space, lots of cables. And we'll see later that maybe digital or more software-defined approaches can help us out here. And the other point I want to make is that the noise we care about, at least up until demodulation, is the noise at the modulation frequency. So noise usually goes down with frequency, or is at least white. And say you're operating at 10 megahertz for your 10 megahertz modulation frequency, the noise there tends to typically be lower than it is at lower frequencies that you might encounter with some of the other techniques. So this can be a very low noise technique. Quick recap. So lots of different ways to lock a laser to a cavity. They all have their pros and cons, simple, easy to implement versus expensive and high performance. And it really just depends what on your specific application. If I didn't know what you were doing, I would just recommend PDH. It's the vanilla default standard technique. The difference between all the techniques is really, what is the reference? Is it a voltage, and like we had inside a fringe? Is it some sideband which has a different interaction with the cavity, like in the Diller locking or PDH? Or is the reference a different spatial mode or different polarization mode? Okay, very good. Again, I'm plotting a PDH error signal on the bottom here and the power transmitted through a cavity, this time on a log scale, so that we can see the sidebands here. And this is all as a function of laser frequency. So this is good. It's very easy to make these plots, but I think it's a little more tricky to really understand what's going on and have a feeling for why they look the way they do. So what I'd like to do now is introduce a different way of looking at things, which hopefully will help you with that. So to begin with, I'd like to introduce the idea of a complex phasor. So often when we talk about sinusoids or oscillators, we talk about them in this kind of A cos omega t plus phi picture. But another way is to think of them as a phasor in the complex plane. So that's what this stick is here, rotating around. So comparing the two descriptions, the length of this stick is the amplitude. How far it is around in the complex plane is the phase. And the speed at which it's rotating is the frequency. And if we take the real part, we get back to this kind of sinusoidal picture that we might be more familiar with. Now, optical frequencies are very high, and you don't often deal with them directly. Like I said, the photodiode really gives you the power that you see due to the interaction of the sidebands in the carrier. So what I want to do now is just factor out the optical carrier frequency. So now instead of this thing rotating at 10 to the 15 hertz or something like that, it's static, and we're going to look at things, everything relative to this. And so you can think of this being like the laser in that diagram. Then in this picture, what's phase modulation? So we sent the beam next through a phase modulator. So in the phasor picture, I said the phase is just kind of how far you are around in that rotation. So a small phase modulation will make your phasor rock back and forth like this. And that's what's shown here. This is our phase modulated phasor here going back and forth. That's very good. But another way to look at it is in terms of a carrier, like a fixed carrier, and then two modulation sidebands, an upper one, higher frequency in blue, rotating one way at the modulation frequency, and a lower frequency red one, rotating in the other direction because it's at lower frequency. And if you take the sum of these in a kind of vector sense, that's what I'm showing here, you'll see that the carrier, the green plus the two sidebands, gives you this phase modulated phasor. If you look closely, you'll see that it's not pure phase modulation. You'll see that when the phasor is off to the side here, it's actually grown a bit. Like it's longer here than it is in the middle here. That's because I've not included higher order sidebands, just to make the diagram clearer and easier for you to see. But if you include everything, you'll see that amplitude is preserved. Okay, the next component on our journey was the mixer. Now, the mixer performs demodulation. It's just a multiplication. And what it really does is take signals from the modulation frequency down to DC. Now, in the phasor picture, what that does is it takes our sidebands, which are rotating at the modulation frequency, and freezes them. It stops them in their tracks. Now, where do they stop? What phase in their rotation? Well, that's determined by the demodulation phase. If you remember, there was the phase shifter between the waveform generator and the mixer. And I said it could be cables, it could be buttons. That's the phase that determines where the sidebands stop. So you have your sidebands rotating, and if you demodulate with one phase, say a cosine, you could get something like this. or maybe with a sign, it might look like this. And I'm going to call these two phases I and Q. These are arbitrary labels. Someone else might have, this might be someone else's I and Q, but this is what we're going to call them in this talk. Okay, so we can talk about electric fields in terms of phasors instead of sinusoids. And in this picture, we can think of the modulation as being due to sidebands. So we have a carrier, and then we add modulation sidebands. We add it up, and that gives us the modulated field. We then modulate things, and that freezes the sidebands. So if we demodulate at the correct phase, we'll stop the system with the phasors pointing like this, and we'll get some picture like this. This will be our I phase. Okay, now for the most important slide in the presentation. This expression here at the top, this is the equation for a Pound-Drever-Hall error signal. Very easy to plot in MATLAB, Python, whatever you like to use. But at least for me, it's not that easy to pull out information of why things look the way they do. So it's the real part of the carrier times the lower sideband plus the upper sideband conjugated. And these phases, this is the demodulation phase. So you can see how changing that rotates the sidebands around. If we now look here to this expression, the real part of Z times W conjugated. And we assume that these are some arbitrary complex numbers and go through some mathematics. We'll see that this is Z dot W. So the real part of Z W conjugate is Z dot W. That's the dot product in the kind of geometric sense. If we look at the correspondence between these two expressions, we'll see that Z is the carrier and W is the sum of the two sidebands along with the phase. So that means that the PDH error signal must be the dot product of the carrier with the two sidebands. So I'll say that again and just with these pictures. The error signal you get from the dot product of the carrier phasor with the sum of the two sidebands. And we can use this new information to maybe get a better understanding of the PDH technique. Okay, so let's look at I phase. So say we have this set up without, this is what we'd have on the detector without a cavity. If the phase of the carrier, okay, here the dot product is 0, we have no signal. But if the phase of the carrier changes a little bit, you know, it was here and now it was vertical and now it's off at a slight angle, the dot product, we will have a dot product represented by this orange arrow. So the I phase is sensitive to the carrier phase. In contrast, the Q phase, the two sidebands cancel out. And therefore, even if the carrier phase changes, we can't detect it because it's carrier dot 0. These two things added together give you 0. However, if the sidebands change size relative to one another, they won't cancel out anymore, and we will get a signal. So I phase gives you carrier phase, and Q phase gives you differential amplitude of the sidebands. Okay, that's maybe a little bit abstract. Let's take it to a cavity example, a PDH example. So I showed this earlier. We're just zoomed in now. We have the response of a cavity and reflection. So there's some dip in amplitude, and the phase goes through 360 degrees as the laser frequency moves through the resonance. For the sake of, maybe clarity is the wrong word, but to make the example easier to explain, I'm going to ignore the amplitude in what follows. If you include it, everything, all the conclusions still hold. It just makes it a little bit easier to talk about and easier for you to follow. So I'm going to ignore the amplitude response now. So ignoring the amplitude response, I'm just going to plot on the top the PDH error signal, and on the bottom, the phase response of the cavity. And this is, again, as always, as a function of laser frequency. So if we look at the I phase, this is the setup of all our phasers that we would see on our photodiode without the cavity. So the recipe is you just apply the response of the cavity to each of these phasers, and you take the dot product, and that's your PDH error signal. So each of these vertical lines represents the frequency of the carrier, the lower sideband, and the upper sideband. So let's apply the response. So the lower sideband has 0 phase, nothing happens. The upper sideband gets 360 degrees of phase, which is, again, nothing. You just come back to where you start. But the carrier gets 180 degrees of phase. So we go from this to this. The carrier is now pointing in the opposite direction. We take the dot product, and the answer is 0. So our PDH error signal is 0 on resonance, exactly what we want. If we detune a little bit below the resonance, again, nothing happens to the two sidebands. The phase is, again, 0 and 360. But the carrier, it has slightly less than 180 degrees of phase. So it used to be here on the dotted line. It's now over here. And if we take the dot product, we have a positive signal. On the other side of resonance, again, nothing happens to the sidebands. But the carrier, it gets more than 180 degrees of phase. So it was here, it's now got more phase, it's over here. And we get a negative dot product. So 0 on resonance, positive one way, negative the other way. This is very good. What about the peak? Why is this the maximum? Well, this occurs when the carrier gets 90 degrees of phase, and the carrier and 2 sidebands are all lined up together. This is where you get the maximum possible dot product here. So that explains that feature. Let's think about the sidebands now. What happens if a sideband is on resonance? You know, you have these extra error signals, if you like, for your sidebands. What's going on there? Well, if we put the upper sideband on resonance, say, our carrier is over here, and our lower sideband is off the page. It's not even shown. So same recipe, we take our phasers, apply the response, take the dot product. Okay, so the lower sideband has 0 phase, the carrier has 0 phase, but the upper sideband gets 180 degrees. So we go from this and we just turn the blue one around 180 degrees, and we'll see again, the dot product is 0. Okay. If we detune a little bit to lower frequencies, again, carrier, lower sideband, nothing happens. But instead of 180 degrees, the upper sideband gets a little bit less. So it's not rotated all the way around to cancel. And the dot product of the green with the red plus the blue is non-zero. In fact, it's negative here. So we get a negative answer. On the other side of resonance, upper sideband gets more phase, rotates around more, and we get a positive signal. So it has an opposite slope to the carrier error signal. What about the maximum, or in this case, minimum? How does that come about? Again, it's when the upper sideband gets 90 degrees of phase. The phasers look like this, and the dot product is at its maximum. You'll note that it's half the size, or I will tell you that it's half the size of the carrier error signal. And the reason for that is here we're taking the dot product of the carrier with only 1 sideband, whereas before we had 2. So the outcome is half as large. A second example now. So this one, just to show you that you can apply the technique to other systems, this is maybe something like absorption spectroscopy. Here, I'm going to look at, this is the response of some imaginary system. And we have a dip in amplitude, so we have an absorption line. And I'm ignoring phase here. I'm saying this system has no phase. And again, this is as a function of laser frequency. So we ignore the phase. I'm just going to plot the amplitude and the error signal, or in this case, it would be a measurement signal. And now I'm going to start with the Q phase. So I'm going to demodulate at 90 degrees and start with the Q phase. And we apply the same recipe. Again, I'm going to put the upper sideband right on the center of this absorber. Our carrier is here, and our other sideband is off somewhere. It's not affected at all. So apply the response. Nothing happens to lower sideband. Nothing happens to carrier. The blue sideband is absorbed, so it's attenuated. It's smaller. So the red and the blue no longer cancel, and we get a big dot product between the resultant with the carrier. So we get a big signal over here. If we move off the center of the line, the sideband is not absorbed so much. It's not attenuated as much. It's bigger. So there's more cancellation. So the resultant dotted with the green carrier is smaller. So you get a smaller signal. And on the other side, it's the same. So you get a classic kind of absorption type feature, as opposed to dispersion that we might have had with the PDH signal. Okay, so detection is a dot product. It's another way to look at constructing PDH signals. And I think, at least for me, it's good for visual people, and it's also easier to think about, oh, what happens to this sideband when it interacts with this system, rather than just typing out equations. So detection is dot product. The demod phase sets where the sidebands stop in their rotation. You apply the response of the system to each of the phasers, take the dot product, and that is your result. And again, I made some approximations, but don't worry, it's okay. Okay, now I'm going to change tack slightly. We're now going to do a little bit of a demo on some real hardware. What hardware is that? So these are the products Liquid Instruments offers currently. This is the Moku Go, which you can win if you fill in the survey. I might do it myself. We have the Moku Lab, and we also have the Moku Pro. So we have something for everyone. And what it is, it's software-defined instrumentation. So all the classic test and measurement equipment you might have in your lab, we have it, but we do it all in one box with a modern interface, modern connectivity. It's really nice to use, and it can really gets you to your results more quickly. So you can interact with these devices via an iPad, on a computer, Mac or PC. And also we have software APIs, which work on Linux and every other system. So Python, MATLAB, LabVIEW, lots of ways to interact. So I'm now going to switch over to, this is the software running on my desktop. You can connect via USB, Ethernet, or Wi-Fi. I'm on Wi-Fi here. And what you'll see when you click on one of the devices is it will bring up 14 instruments. So we offer 14 different instruments currently. It's growing all the time. The latest time and frequency analyzer came out in about April. So we update every few months, and things get better over time. So if you want, say, an oscilloscope, you click a button, you have an oscilloscope. If you think, oh no, I want to see the spectrum, you click on the spectrum analyzer, and say 10 seconds later, the box is now a spectrum analyzer. Very nice, very easy to use. I'll demonstrate that by looking at the laser lock box. So we're talking about laser locking today. This is our laser lock box product. You open it up, it's got a nice, clean, modern interface. If you can use a phone, you can lock a cavity. So our signal comes in here, and this is our digital mixer. So it's a pure digital device. You don't need to worry about the non-linearities, I and Q not being at 90 degrees, and all these typical things, components aging over time. This doesn't age over time, all digital. We have a built-in modulation source and phase shifter, and then it goes into a filter. So just to show how easy things are to do, if you want to change the corner frequency of this filter, you don't need to solder. You just click and drag and you can move it around. If you want a different style of filter, click, it's done. You want a band stop, you get the picture. You can also upload custom filters. In terms of second order sections, you could just copy and paste from MATLAB, Python, or you can load it from a file. Then we offer a set point if you have some residual amplitude modulation, for example. If you just don't want to lock perfectly on resonance, you can include that there. Then we have two paths for feedback control. We call them fast and slow. So this could be like temperature control, or perhaps like PZT and temperature. It could be PZT and EOM. It could be a PZT and a voice coil, any sort of split that you might be using. And again, it's so simple to set up your feedback. You can just let's pick on, say you want just simple 1/f. You can drag it around. You want to add some saturation at low frequencies while you lock, you can do that. And again, all this is totally scriptable. You can set things up in the GUI and then run repeated measurements using a script. You can automate things. Very nice. Then we offer integrated scan. I think one of the benefits of the way we do things is the integration. So if you want to, your modulation source is here. If you want to scan across your resonance to optimize phase or just to save some data for fitting, the scan is already here. And then on the output, we offer some limits just to protect your hardware. In addition, there's an integrated oscilloscope. So we have probes. You can put your probes, you can look at the input, you can look at the output, error signal, control signal, and it's a fully featured oscilloscope. There are measurements, triggering, everything, all within the Laser Lock Box instrument. Sharing data is as easy as clicking a button, hit export. It's off in the cloud. We also offer a data logger for taking data over perhaps a longer stretch. And maybe the final thing I want to mention right now is we have locking stages. So when you lock a cavity, you might want to start with low gain and then increase the gain or change the loop shape slightly. We have different stages which you can engage in series as you go. And there's one more feature, but I'll show you that in a minute. It's my favorite one. Okay, so that's the Laser Lock Box. I'm now going to go on to a demonstration on a Moku Pro. And I don't have a laser and a cavity here. And I was a little bit disappointed about that. But then I thought I can use our multi-instrument mode to emulate a complete locking system. And I think it gives a great demonstration of the power of these devices. So in addition to our 14 instruments, we also have multi-instrument mode. What is that? Well, what it does is it lets you, on this model, have up to 4 instruments running at the same time. So they can run in series. You can connect them up to make a bespoke measurement system, or they could be in parallel. You could have 4 signals going into 4 different things, totally unrelated. So for example, I could have 4 laser lock boxes. I could have 4 lock-in amplifiers, or I could do what I'm doing now. So I have a laser lock box, obviously, and to mimic a laser, I'm using a waveform generator. If you think what is a laser, it's just a kind of monochromatic oscillator. So that's what I'm doing here, and I've enabled frequency modulation to tune my laser and also to imprint sidebands upon it. Then I need a cavity. So the cavity just has some complex response on the laser. So I can do that with a filter. And indeed, what I did was I made a filter that looks like this in MATLAB. So these are my two resonance dips for an FSR and some phase. And then I just imported those coefficients into our digital filter box. So that's my cavity. And then my detector, my photodiode is, if you think what a photodiode does, it really just squares and low passes the signal. So I'm using our lock-in amplifier to do that. It's a little bit like, I don't know, using a JCB to put up a picture or something. It's not quite the right tool for the job, but it does what we need it to do. And then if we go into our laser lock box, you can see that all we can change the phase digitally to optimize our signal. So actually, since we've got the oscilloscope, what we can do is we can enable a math channel, set it to the slope of the signal. And then if I make a measurement on the maximum of the slope, I can tune the phase to give me the biggest slope. So something, I don't know, something about there. Let's get rid of that now. I've just got a simple 30 kilohertz low pass filter. And then for my controller, I've got a 100 hertz 1/f, and I've got some saturation here just while we lock. And now what I want to do is show you my favorite feature. This is called Lock Assist. So what it does is it integrates tightly the oscilloscope and the scan. So when I change something on this oscilloscope, it changes the scan of, say, the PZT across your resonance. And it then will find zero crossings. And if you want to lock, let me just switch this to our reflected power. If you want to lock on one of these resonances, all you need to do is click on it, the zero crossing you like. So we click here and we're locked. I can then go to my locking stages, engage the low frequency gain, remove that saturation, and that's it. Now, just as an example, if we consider the scan not to be something that's, you know, moving our laser across our resonance for diagnostic purposes, but rather as a source of noise, I can turn on the scan while we're locked, and we'll see that nothing really happens. And the reason for that is because if we look at our control signal and we zoom in, the feedback loop is making the control signal is putting out the opposite of the ramp to cancel out and keep us on resonance. So with that, I'll come back to our presentation. So we saw the laser lock box. Hopefully you saw the advantages of the way we do things. So it can be more cost effective because everything is in one place, and it's faster to try things out, to get from an idea to a result. Everything's scriptable. You don't need different APIs for different boxes that you have in the lab. Noise can be lower, particularly at low frequencies after the demodulation. Noise still matters. So if you care about low frequency drifts, usually digital systems will have better noise there. We saw multi-instrument mode, so it's not just, you know, one box that does multiple things. You can do multiple things at the same time, and it's very useful. We saw how we could use that to mimic PDH setup. And then we saw the laser lock box. Very nice, very easy to use, and customers really like it. Okay, so with that, I'll just thank you very much for your attention. I hope I conveyed, some of my excitement for this product. The software I was using, it has a demo mode. So I have real hardware on my desk, but if you're, thinking about this, you want to try it out, the software has a demo mode, which you can find here, liquidinstruments.com, or at this QR code. So it would be great if you wanted to try that out for yourself. You can go and do it. Thank you very much.